Welcome to the Ada Lovelace Day podcast. I'm Sue Charman-Anderson, and this month I'll be talking to Dr. Jess Wade about how plastic electronics are revolutionising solar power. And author Robin Sloan talks about one of his favourite science fiction writers, Ann Leckie, and about the symbiotic relationship between science and fiction. We'll also take a look at an invention that powers your mobile phone, amongst many other things. And we have the winner of March's competition, who will receive a signed copy of Dr. Helen Chersky's new book, Storm in a Teacup. So I'd like to welcome this month Dr. Jess Wade, who is a researcher at the Centre for Plastic Electronics at Imperial College London. Hi, Jess.
Hello.
I'm going to start with the obvious question, which is, what are plastic electronics?
So it's super exciting. We're in a decade of a revolution in the electronics that we use in our homes, in our lives, and we're going to use them to change what we do in the future. So as everyone who listens to this podcast is probably well aware, the world is warming up and we have a massive issue with solar and renewable energy and the uptake, and it hasn't really been quick enough. There's an awful lot of reasons behind that. So if we start with solar panels, there's not a huge increase in the number of people using them despite huge advances in the technology. In the current state, the materials that we're using are really, really brittle. They're really, really hard, the kind of materials that we make solar panels out of. They're also incredibly ugly, the solar panels that we use in people's houses today. They're incredibly labor intensive to make, so it takes almost as much energy to make a solar panel as you can currently get out of them. And they're really, really expensive. We're not using them a lot in the UK for obvious reasons. We don't have sun most of the year and all of the above. It's also very difficult to input the power that you generate from your solar panel back into the grid, back into the system. There's also a massive issue with politics and getting these things through governments who may or may not believe in climate change, may or not believe in the causes of the world heating up. And so we've got a massive crisis on our hands where we have technology, but we're not doing it. Despite all of that, the current market for solar panels is about $42 billion. Instead of using the kind of technology that we are familiar with in solar panels, in the Centre for Plastic Electronics, we're trying to make electronics that are cheap, flexible, and we're doing that using plastics. So how do they work? In light emitting diodes, in solar panels, in transistors, we have something called a semiconductor. And I don't want to patronize your audience by trying to explain what a semiconductor is, but it's basically halfway between a metal and a plastic. So obviously in a metal, the material is conducting all the time. The electrons are in the conduction band and they're just whizzing along happily. In a plastic, there's a massive, massive gap between the conduction and the valence band, so where they can conduct and where they can bond. And that's really, really difficult to overcome, and we can't actually do it at room temperature and pressure. In a semiconductor, there's a smaller energy gap, and that energy gap is so, so important for the kind of devices that we make. So if we're making a light-emitting diode, that energy gap tells you the color of the light that will come out. Or if we're making a solar panel, that energy gap tells you the color of light that it will absorb and then use that to translate into electricity. And that's super exciting. So inorganic semiconductors, the things that we use normally, like silicon, gallium arsenide, have a fixed energy gap. And that energy gap is pretty good for the incoming light from the sun, which is all right, great for them. But the bonds between the atoms in those crystals are so, so strong that it takes such high temperatures and pressures to kind of pull them apart, that it's incredibly expensive for one, and it also means that we can never ever make a flexible device out of them, because if we tried to do anything with plastic, we'd melt the plastic surface that we were putting them on. Organic semiconductors, on the other hand, which are carbon-based polymers and small molecules, so kind of groups of atoms collected in these structures that you probably remember from chemistry A-level or chemistry GCSE or even your university degree in chemistry if you're a chemist. But these materials have much, much weaker bonds, and there's a special arrangement of carbon bonding that I can tell you a bit more about if you want, that allows these things to become semiconductors. So if you imagine a polymer chain, we've got alternating single and double bond. These things are conjugated. If you can remember benzene, the structure of benzene, that funny kind of delocalized orbital of electrons above and below the plane, I always used to draw it in chemistry like a bagel or a donut. I think I just liked drawing bagels and donuts, but you have these little electrons that are homeless. They don't belong to any particular carbon atom. They're whizzing around this ring structure. If I've got my long polymer chain, they're wiggling all along there. And that means we can get these things to conduct, which is super, super exciting. Also, because the bonds are much, much weaker in these carbon-based polymers and small molecules, we can dissolve them in solvents, in the kind of solvents that you have in your science lab or in your cupboard if you've ever taken nail polish off, things like acetone, things like chloroform if you're a big fan of Breaking Bad. And we can make conductive inks. And conductive inks are awesome because then we can print them. So we can print them using conventional printing techniques, the kinds that people already have. So there's a huge solar cell printing press in Swansea. And it's incredible. And it's all using technology that we use all the time to print newspapers and stuff like that, and printing these plastic solar cells onto massive sheets. The band gap, that energy gap that we were talking about in semiconductors, can be tuned with the chemistry that we use. So we could put in different atoms, we could change the structure of the polymer, we could use different materials. And then we can change the light that they emit if it's a light emitting diode, or the light that they absorb if it's a solar cell. So we've got a really fine tuning of that. And the kind of devices that they're used in boast themselves, pride themselves on the fact that they have super, super high contrast, beautiful colors, super, super great absorption. And that's because we're tuning it using chemistry, not using crazy, ridiculous filters that block out some of the light. So what we've got is we've got this conductive ink that we can print kind of at room temperature. We can print incredibly thin layers onto a flexible substrate and then make a device using that. So we've got kind of a double layer of plastic. We've got the plastic that's doing the absorbing or the emitting, and then we've got the plastic that we've got as our surface. And that's basically what plastic electronics is. It's using plastics, functionalized plastics, using them on plastics to make flexible electronic devices. And the applications are massive. So it's not just in things like solar panels, but also roll-up displays, foldable displays, stretchable displays, wearable electronics, bioelectronics. Because obviously it would be perfect if you have a flexible electronic circuit. Why not try and interface with the brain or something where you really want to be bendy and kind of plastic and meldable? But also because I think in science, I've come to realize that it's much easier to get grants if you say bio on anything. So everyone is going down the bio bandwagon. But there have been huge advances and developments in this technology recently. And I think from a kind of UK perspective, it's super exciting too. So I know you obviously have listeners all over the world, but we're really good at this science in the UK. The company who make probably the best light-emitting polymers in the world was a spin-off from Cambridge. The company that are currently making a flexible e-reader was a spin-off from another university. These things are all happening, and it just feels like a really exciting buzz. It just captivates you. It's a privilege to be part of it, and I feel like it's something that's really, really worth contributing to.
That sounds really kind of very much like some of the technologies that have been sort of talked about in the past as being way in the future are maybe slightly closer to happening. I'm thinking about the whole kind of flexible e-reader, which is a concept that's been around for a long time, but has felt like it's very far away. So you're saying people are working on this right now?
People are absolutely, definitely, 100% working on it right now. There are massive issues with translating this technology to market, which I guess is what you're saying. The issues are both research focused, trying to get these materials to work, trying to get them not to degrade. So if you've ever left anything plastic out in the sun for a while, you know it goes a bit funny, it starts to bend, it starts to not be what it was before. And that's obviously not great if you're a solar cell. So if you're making a solar panel out of a material that absorbs light, you don't want it to then deform and stop absorbing light when you leave it out in the sun. So a lot of our research is focused on getting these things not to degrade, finding kind of capping and protecting layers. The organic light emitters are in, so they're in Samsung Galaxy phones, they're in the OLED display, if you've seen an advert for an OLED display. It's currently incredibly expensive, so OLED stands for organic light emitters. They're very, very expensive, and they're expensive because we've not quite got the inks at the lowest cost they could be yet. We've not quite optimized these structures, and we're still putting in glass layers. We're still putting in gases so that these things don't degrade when they're in ambient conditions. So researchers are trying really, really hard to find ways to do this. The really exciting thing that I am currently working on, my current project, is making light emitters that emit circularly polarized light. So in current organic light emitting displays, you emit unpolarized light. So you've got all different kind of polarizations mixed up in there. And we have to put loads of filters in the way of the light emitters so that the light doesn't reflect off the back electrode. So you have your electrodes, you have your light emitting material, your organic light emitting material in a television. It's coming out, it's coming to you. But so that you don't see the reflection of that organic light emitter in the back electrode behind your television, we put in a series of filters to stop that from happening. And what happens when the light goes through those filters is you lose an awful lot of your light intensity. So you're blaring out this really high intensity, beautiful colored light, but you're losing it in these filters, which is obviously costing you money. So now we're working on materials that emit circularly polarized light, which when it goes through these filters won't lose any of its light intensity because the polarization is tuned to move around so that it fits through these filters. If you kind of imagine arrows pointing in different directions, it slots really nicely through these different filters so you don't lose any intensity. So that's focusing on designing new materials that can overcome barriers that we've seen when we've put our technology out there. The other massive problem is political, right? So organic solar panels, organic sheets of solar panels, precisely plastic sheets of solar panels could be in. We could have them. They have them in Brazil. They're using them in developing countries across the world. Implementing this kind of technology in the Western world is really, really difficult. And I think it's because we're still kind of invested in old technology. We're still doing things like using oil and gas, although I know in the UK we're using a lot more wind power, which is great. But what we really need is a kind of big political strategy to say, okay, we've got this, we've got the research, we are bloody good at it, and now we're going to roll it out and we're going to do it and we're going to make architects use it, we're going to make designers use it, because it could happen. There's a super exciting thing. You can functionalize a window. You can get your current window, coat it with an organic salt, which is a transparent luminescent solar concentrator. And this organic salt will act to absorb the non-visible light, so the ultraviolet light and the near-infrared light. Then it will glow at a different wavelength, so it will glow light at a different wavelength that we can't see, or maybe infrared light or ultraviolet light again. And then this will be guided to the edges of the glass, to the edges of your window, and then absorbed in a different solar cell. So your bit in the middle is just absorbing light and emitting light at a slightly different wavelength. It's then transferring this to the edges where we've got a solar cell. So you've truly got a transparent window, which is great. You can see through it. You're not losing anything. But you've also got a solar cell working there, which is brilliant. And if we could come on board and say, okay, so maybe it's a little bit more expensive than having normal glass, but we're doing something that's really, really good for the environment and it's super exciting, then I think it could happen. All of these things are just like ready to go, but just not taking off. The one in solar technology, which is super exciting, is actually a spin out from Oxford. I don't know if you've heard of perovskites or if you've had someone on here talking about perovskites, but they are these kind of crazy crystal structures. They were only discovered that they had this kind of functionality a few years ago. So in probably about 2011, 2010, that kind of time. It's super new. They are a hybrid crystal, so a hybrid organic-inorganic crystal with containing currently some lead halide, which isn't great. No one really wants to be working with lead, or you don't want your solar panels to contain lead. But they're incredibly efficient. Over the past kind of 5-10 years, they've absolutely taken off. They're approaching the efficiencies that we have of silicon solar cells. And this is super exciting. So previously, we were hitting about half the efficiency of solar cells that we have with the organic materials. Now we've got these hybrid organic-inorganic crystals. We're going very, very close in a very, very small amount of time. And basically every researcher I'd say across the whole world is trying to make this happen, trying to make this research come to reality. And there's a spin out in Oxford perovskites or something like that, who are doing phenomenally well with it. So you really feel like it's exactly what you said. We're on the edge of this thing actually capturing and actually taking off and happening. And it is absolutely fascinating to watch it happen.
Yeah, I mean, it really does sound like the opportunities there. Because if you've got solar that is flexible and cheaper, then, we could start using it in places where previously you wouldn't put up a solar panel. I mean, you could coat buildings with it, surely.
It'd be brilliant if this kind of technology could be used on buildings, on boats, on roofs, on schools, but it would also be great if it could be used in the developing world. And that's where I think it's really, really exciting. So you can print a massive flexible sheet of solar cells and you can roll it across the desert in Africa. You can take it to a remote Indian village. because what these things are brilliant at, and what renewables are brilliant at in general, is they don't need to feed into a grid. You don't need to plug your thing into a whole system of electronics that's connecting to somewhere millions of miles away. You can just set up your solar panel on your roof and get power, which is really, really great. The really difficult thing, and actually there's a friend in my former PhD office and now research lab at Imperial, who is looking at putting these things in places like Rwanda. And the really tricky part is educating people into how to maintain and look after them and use them. So you can't just get this great technology and say, hey, we're geniuses, we've made a flexible solar cell. Let's just take it to a desert. Let's take it to a village who don't understand anything about solar cells, because they won't know how to look after it. So what we need to do is we need to develop the technology. We need to work with people in these places so that they're aware of what we're doing and know how to use it. What's great about these things, what's great about these solar panels is, say one part of the sheet breaks, say one part gets damaged, say anything happens, you can just print a new bit. And if we could set up these little labs in these different kinds of places, we could keep them working, they could keep going, they could keep surviving, and it could just keep getting more exciting as we develop newer inks, as we develop materials that last longer and more efficient. So I think you're right. I think you could just print these and they could be useful anywhere. And that's why they're so exciting. Every flexible surface outside could become a solar panel. Every roof of a car could have these things wrapped on the top of it. The lightweightness adds something as well. So not just having something that's kind of plastic and bendy, but having something that's super, super light. You can make clothing out of it. You can make backpacks out of it. And I really think that's where this thing is amazing.
Yeah, I mean, it would completely change how we think about electricity. You could carry your own electricity with you.
You can carry it with you, and crucially, you can borrow from the manufacturing processes that we've already developed. You're not inventing anything new. You're getting something like the inkjet printers that people have in their houses now, and you're taking out the ink cartridge and you're filling it with an ink that can semiconduct. And that just seems absolutely ridiculous, right? That you can do that, but people do it. It works. And so it is completely here and it's completely happening.
So in your sort of day-to-day work, what are you focused on doing?
I don't know how familiar you are with Imperial, but I think working at somewhere like Imperial is a complete blessing. So we have massively successful, huge and exciting engineering faculty with 10 different groups of engineering inside. Then we have the Faculty of Natural Sciences, which has physics and chemistry, which are the ones that I'm mainly interested in, and then maths and biology. And then we also have kind of postgraduate business school and a medical school. But it means that we have people who we can collaborate with and network with who are all in the same postcode at us at the same time. So I work as a physicist with chemists from the chemistry department, with chemical engineers, with material scientists. The chemists kind of do some crazy cool synthesis, come up with some ridiculous cool new molecules, polymers. Maybe it takes them an entire PhD. Maybe they've just got a few milligrams of exciting stuff that they've been given by a collaborator somewhere, which is just ridiculous. And then we meet and you take this amount of material and you go and make a few devices. You do a few measurements to look at. What I'm actually super interested in is how the molecules and how the polymers are behaving in these thin films. So which way are they pointing? What kind of order are they in? Are they the same throughout the whole thickness? Is something happening when you blend them? So we do an awful lot of kind of material characterization, and we have really nice pieces of kit to be able to do that. And you can work between physics and material science, and it's super great and collaborative because everyone wants these things to happen. Everyone wants this research to become reality. And then maybe you make your device, it doesn't work so well. Maybe something's really, really great. You go and tell your chemist friends, you develop it a bit further. So you really get a privilege doing this kind of research to work between loads and loads of different groups. And now with this interest in going bio and doing this, we're working with bioengineers, which is super, super exciting too.
Excellent. So how did you end up working with plastic electronics?
Yeah, I think that's a really good question. In about my third year of my degree, so I started off before Imperial, before doing physics, before this took over my entire life. I went to art school. I did an art foundation at Chelsea and I loved it. I was always going to apply to do physics. So I think it was just kind of relief after my A-levels. And also I've always been super fascinated by the creative world and still am, and science lets me be even more creative than I could have ever imagined. But then I started in physics at Imperial, and in about your fourth year you get to choose a research project to do for a master's. And I had an incredibly lovely lab partner at the time, and we just went for this interview with this supervisor who I think I saw kind of spark there. There was something very exciting about the research group that she had. And I thought this is something that could be super cool. And I didn't realize, I spent that entire summer between my third and fourth year that, this old thing, university students get huge amounts of holidays, and we do. But I spent that entire summer in her lab, becoming more and more familiar with the technology, with how we were doing the printing, getting my first clean room gown, getting all this access to lasers, to spectrometers, to glove boxes. And I was so excited. I was buzzing. I was in every single day. I was cycling in at like 5:30 in the morning to be able to do these experiments, to get data, to see what was happening. And I think that summer really cemented to me that how much I loved research and what a privilege it was to be able to do it. And I then applied in about my fourth year, and I had just completely fallen in love with both the research and the group by then. And I really liked being part of something that was exciting and progressive. And I felt like we were working together and really trying to help each other find new solutions to coming up with answers. It's exactly what you wanted research to be like. And obviously that changed throughout my PhD as people graduated and people left and the office changed and people got headphones because I used to talk so loudly and talk so much in the office. But it is still this incredibly magical time, the beginning of your research career, when you're really learning who you are, what you're interested in, and you're kind of making a name for yourself. And I think that doing this kind of research has taken me to places that I would never have dreamed of. So not only within my own mental state as I stare at a spectrometer for 10 hours straight, but also I've been to South Korea and I've been to China and I've been to Brazil. And that feels ridiculous. Like I've been there not because I wanted to go on holiday there, not because I saw some cool pictures on Instagram, but because someone there wanted to hear from me about the kind of research I did. And I think if you told my 10-year-old self that, I'd have laughed in your face and had no idea what you were talking about. Like it's just, there's something that keeps you going in science. There's something that keeps you going when you're doing something that you completely love. And I found it.
That's fantastic. That was my dream when I was at university. It just took me slightly longer to find the thing I love, I guess. What's on the horizon for you? What is getting you excited about what's coming up?
The things probably that I've already mentioned. So circularly polarized light emitting materials, super, super exciting. I don't think that they've quite been optimized yet. We've got a whole range of new molecules to play with, a whole range of new polymers, a whole range of characterization techniques to get used to. And kind of the processing is super fascinating. So I don't want to end this by saying, oh yeah, it's really fun to look at the way we process a film after we make it. Kind of like cooking, right? So we make our device and then we essentially put it in an oven for half an hour to let all the materials wriggle around and get to their most thermodynamically stable state, the happiest arrangement of atoms that you can physically have. And I think there's a huge amount of understanding what's actually going on in those transitions. There's a big movement towards in situ spectroscopy, in situ measurements, doing things when you're heating them up, when you're cooling them, when you're putting them under pressure. These kind of things are happening. And I think that's super exciting for one. I think the progression to bioelectronics, making things that can help people. So I started probably my PhD making transistors. Transistors are great. They're used in everything. You have thousands and thousands of them in your mobile phone, but I wasn't super excited by it. And I couldn't quite put my finger on it until I started doing something like solar and started making these materials that, you hope one day could actually help. I hope these things get used in people's houses. I hope they help people in the developing world. And I think that's where, being able to be useful. And that's where bioelectronics is super, super exciting for me. I think also the stretchable market. So probably going away from entirely flexible, because you don't need a television that you can scrumple up and put in your pocket. But having some kind of stretchable electronic circuit, having light emitting diodes that in some kind of fabric that can stretch would be really, really awesome. What I'd like to see in science and engineering in general is more collaboration with the wider world around us. So obviously we collaborate great within ourselves and we talk to everyone in all of these different departments. But talking to designers, I think, is really, really crucial, and talking to architects and making that work more. So making these technologies be used in modern buildings, making the government say, hey, you know what, you need to do this. Working with people who are designing clothes, designing technology and saying, this is how you could make it more functional. This is how you can make it more bendy. And I think that's what the real challenge lies. So my friend actually had webinar yesterday for an hour about why wearable technology hadn't taken off yet. Why hasn't it happened? And I think it's because people like us are sitting around in science labs like, oh yeah, everyone would really want to wear this bendable light emitting diode display, when really everyone else is looking at it like, that is hideous. So we really, really need to work with people who can design great looking things and ergonomically sensitive things so that people actually want to use this. And I think that's where the technology is going now. So it's going towards biological applications, and it's going towards working with people who can make it something that people want to buy. So at Imperial, we have this amazing course, which if I was an undergraduate, I would do in a quick minute, which is design engineering. That's joint between engineering at Imperial and design at the Royal College of Art, which is like 200 meters away, which seems like the perfect interface of scientists, this hard science knowledge, this hard engineering knowledge. We know these materials, we know this fact, and people who actually know how to design products people want to buy and use. And so I hope that the world goes more towards that, more towards these kind of collaborations, and more towards this really openness with the people who are designing the systems of the future.
Yeah, because I think C.P. Snow's Two Cultures is so embedded in the way that we think about science and the humanities. We really need to get past that. It's essential that there's more cross-pollination and collaboration between the arts and the sciences, I think.
Yeah, I think it is. And I think obviously it starts at school, where you have these very, very rigid timetables. And I'm not blaming anyone within a school, because I know how overstressed and overworked teachers are. But I think you have these timetables that separate maths from physics, from chemistry, from biology. You're told some weird secret when you get to A-level that maths and physics are basically the same thing, which is some massive lie. And then you go to university and you still got it a bit for your undergraduate, increasingly less so as you progress through your undergraduate. And then in research, they're just like, oh, by the way, all of that was rubbish. We work with all these different people all the time. I had more chemists in my research group in a physics department than I had physicists. We needed to understand this about engineering. We need to understand this about processing. We're doing exactly the same things, but calling it by slightly different. And I really, really think that the creative world, the arts, contributes so much. You can't publish a science paper or write a science book if you can't do English, right? You can't go to a conference in France if you have absolutely no understanding of French. Yeah, you're right. You're entirely right. We just need to make it happen more. We need to put ourselves slightly out of our comfort zone. And yes, the meetings may be incredibly uncomfortable at the beginning, but you can get so much productivity, something brilliant and beautiful made out of it at the end, that I think it's worth it. But I do genuinely believe that it is starting to happen. I don't believe it's happening in schools by adding an A to the incredibly infuriating acronym STEM to turn it into STEAM. I think it's happening completely organically because designers really want to use cool materials in the kind of stuff that they're doing. And I think scientists are making some really, really cool materials. I don't know if you've had a chance, because obviously you're incredibly far away, but at UCL, they have a place called the Institute of Making. It's insane. Like it's every student and staff member of UCL gets access to this institute. It's led by Mark Miodonik, the incredible material science master. And you get trained in 3D printing, you get trained in woodwork, you get trained in metal design. You can go in there. It's a space where, as anyone at UCL, as a history of art student, as a psychology student, you learn to make and you learn to create, and you make things for your PhD, you can make things for your mum's Mother's Day present, you can do all of these different things. And I think that's where we're going. We're going towards this world where we take things apart and we tinker and we say, I want to make this happen. I want to do X with this technology. I want to work with you. And I'm super excited by it.
I've been lucky enough to take a look around that space, and it is amazing. And I wish there were more spaces like that.
I think it's happening.
Yeah. I think we are going to see a change, because I think people are seeing how exciting those spaces can be and how productive they can be.
Yeah, we had a great show on the BBC over Christmas called Big Life Fix. And it got these kind of engineers and makers and hackers into a room, and it gave them each week, it had 3 challenges. It was only on for 3 episodes, which was massive sadness, but it has been commissioned for a second series. So they had these 3 real world challenges from people across the UK, and they were things like, all my sheep are being stolen, or boy who had a terrible skin condition and couldn't touch anything but wanted to be a photographer. And these hackers and engineers and makers came together to make the products, to design the systems that would allow these things to happen. And it was so moving and so brilliant, and they were so bright and creative. And you just thought, We need this in every school. We need design technology not to be a ridiculous subject where you make identical jewelry boxes, but you're designing some kind of system that lets someone who has no sense of touch be able to not touch a scalding pan and not feel anything. I just hope, I really want this to be a world where we help each other out more, and we do that by enabling using technology.
Well, that is the perfect note to end on. So thank you so much for your time, Jess. It's been great talking to you.
Thank you.
You can find out more about Jess on her website at makingphysicsfun.com, and you can follow her on Twitter at Jess Wade. If you're curious about the work of the Plastic Electronics team, you can find out more about their research at imperial.ac.uk/plastic-electronics. And as usual, we've got all of Jess's links and her bio in our show notes. Our podcast is made possible thanks to the generous support of ARM, our exclusive semiconductor industry sponsor. You can find out more about ARM's energy-efficient microprocessor technology on their website at arm.com, and you can follow them on Twitter at ARM Holdings. If you'd like to join ARM as a co-sponsor of our podcast, then please email me at suw@findingada.com. Now it's time for our invention of the month, this one connecting torpedoes, avant-garde music and Hollywood glamour. Now, during the 1930s, tensions in Europe were rising as the Nazi Party gathered strength. In Austria, Friedrich Mandl, an influential fascist, was selling arms to anyone who wanted them, including the Nazis. He was also investigating the use of radio to control torpedoes. Mandl liked to control things, including his beautiful wife, Hedwig, whom he took to business meetings. Hedwig learnt a lot about military technology as she sat silently in Mandl's meetings. She knew, for example, that it's easy for an enemy to disrupt a radio-controlled torpedo by broadcasting noise on the same frequency, jamming the signal. Eventually, Hedwig fled her unhappy marriage, escaping to Hollywood where she became Hedy Lamarr, star of the silver screen. But she didn't forget about the torpedoes. Realising that the Allies' radio-controlled weapons were at risk of jamming, she worked on an idea to stop the Axis forces interfering with Allied signals. To give it its full name, frequency hopping spread spectrum is a technique for protecting a radio signal by rapidly changing which frequency it's transmitted on, spreading the signal out over a wide band of the radio spectrum. Both the transmitter and the receiver know which frequencies will be used and in which order, but the enemy doesn't, making it difficult to jam. Additionally, spread spectrum signals are harder to intercept. At a Hollywood party, Lamarr met avant-garde musician George Antheil, one of the first people to compose music specifically for a player piano or pianola. Lamarr told Antheil about her idea for a torpedo guidance system which would switch frequencies in a random pattern. She thought that Antheil could solve the last piece of the puzzle, how to synchronise the transmitter and receiver. The two came up with a solution: 2 paper rolls with identical patterns of holes, one for the transmitter and one for the receiver, just like small pianola rolls. They even used 88 frequencies, the same as the number of keys on a piano. In 1942, Lamarr and Antheil were awarded a patent for their secret communications system. But rather than develop it commercially, they attempted to give it to the United States government to help with the war effort. The Navy, however, did not take it seriously, and their invention was not used during the Second World War. Lamarr offered to lend her inventive mind to the government, but was rebuffed and told to go back to Hollywood and use her fame to raise money. She did, raising $7 million. It wasn't until the 60s, when the patent had expired and digital technologies made implementing frequency hopping easier, that Lamarr's idea was finally recognised as important. Spread spectrum is now used in a wide array of communications technologies. So the next time you use your mobile phone, connect to the internet over Wi-Fi, or listen to your Bluetooth speaker, say a little thank you to Hedy Lamarr. So I'd like to welcome to the podcast Robin Sloan, the author of the novel Mr. Penumbra's 24-Hour Bookstore. Hi, Robin.
Hi, good to be here.
It's lovely to have you on. Now, we're actually going to go a little bit off-piece this month because we're not going to be talking about a woman in STEM per se. So who are we going to be talking about?
We are going to talk about a writer, a novelist named Ann Leckie, who is one of the greats of modern science fiction.
So I'm really excited to actually start talking about women in science fiction as well as women in STEM, because certainly as a youngster I read a lot of science fiction. I think there's a lot of cross-pollination between fiction and science.
I think that's right, and this is true for so many people in science. Interesting fields like economics, psychology, sociology. I think if you peel back the layers of the onion, you will often find, whether these people remember it or not, a pretty formative science fiction reading experience in their past.
Ann Leckie, why have you chosen her?
Well, I've chosen Ann Leckie because she's just one of my favorites right now. She's doing this interesting thing of sort of writing new classics. It's easy to go back to the great canon of science fiction and, find all these great voices. But I'm always interested in the people who are adding to the shelf. And there's no question that one of the key people doing that right now is Ann Leckie.
Her debut novel really made a real impact, didn't it?
That's right. It's called Ancillary Justice, and if I'm remembering right, I think it won all the awards. You don't even need to enumerate which science fiction awards it won, because it just won them all in the year that it came out. And I found it just by chance. Somebody, I think, mentioned it on Twitter or elsewhere on the internet, and it's just the basic appeal of a book. I liked the title. I liked the cover. I read the short description and thought that sounded good, and so I read it, and it blew me away.
Wow. And without spoilers, what's the story?
Right. So no spoilers here. This is all sort of set up in just the opening scenes of the book, and truly it's this setup that makes the book so remarkable, and I think so interesting to talk about in this context of science fiction connecting to STEM and all sorts of bigger things. So this is set in the far, far future. This is no mere, cyberpunk near future. This is a whole different civilization that kind of spans the galaxy, probably tens of thousands of years from now. And as the book opens, our protagonist is actually a sort of artificial intelligence mind that's in control of a whole ship. This huge ship that kind of goes coasting from planet to planet, doing things for this far future empire. And the mind behind this ship, of course, has access to all the ship's sensors, and it can see this incredibly rich, multi-layered, deep, nuanced vision of the world around it, of the universe. And in addition, it has hundreds and hundreds of bodies that it can act through. And the exact nature of these bodies and where they came from and, what are they is kind of part of the plot that unfolds. So I won't ruin that. But suffice it to say, this mind has an incredibly rich vision of the world and incredibly rich ways of acting in the world. And then, in the book's opening moments, there is treachery, the ship is destroyed, and this mind is essentially trapped in one of these bodies. And of course, so it's a human body, and so suddenly this mind has an essentially human experience of the world, and that's how the book proceeds. We follow it through this adventure, trying to, escape to safety and figure out what happened and, maybe exact some kind of vengeance. But the dramatization of a normal human viewpoint as being sort of woefully limited and kind of sad, at least from the perspective of a sort of a vast artificial intelligence, was to me totally provocative and interesting and imaginative. And I just think that as the foundation of the book leads you in all sorts of interesting places.
I think for me, the thing that is interesting is that she's taken a very standard sort of space opera-y setup and then done something so radically new with it.
It's, there are spaceships and, a galaxy-spanning empire and all that good stuff. But it is a book about minds and a book about perspectives, strange minds and strange perspectives. It's not only the experience of this, ship AI now trapped in a little meaty human being with 2 arms and 2 legs and 2 eyes, the leader of this empire, this future space empire, it's not the dark shrouded figure of Star Wars. It's not a sort of Julius Caesar kind of, charismatic leader. Instead, it's one of the greatest characters in sort of modern science fiction, at least for me. Her name is Anandar Mianai, and she's not just a her. She's actually a multiple. I don't even know how to say it. It's a good sign when you don't have words for it. It's one mind spread through many, many bodies. Because of course, how are you actually going to manage, a galaxy, a sort of a galactic scale empire? You're not going to do it from like an office on Earth. You're going to have representatives spread throughout, the empire. And in this case, they're not merely representatives. They are actually fragments of this person. Anyways, that sounds strange. It is strange. It's also great and new and weird. And again, it's about minds and new kinds of minds. And to me, that's truly what sort of distinguishes it from the space opera tropes that we're used to.
Yeah. And I mean, we're used to scientists becoming authors. I mean, that's a fairly well-established thing. But Anne actually wasn't a scientist before she became an author. So it feels to me like, that she's actually really grasped some of the quite radical thinking about sort of minds and bodies and that. But that's not her background.
Yeah, and I think that's maybe what the literary mind can bring to bear to these things. Good fiction, I think, of all genres and sort of levels, tends to end up being about a mind or consciousness of some kind and has some question about that consciousness. It doesn't have to be the question of like, what would it be like for an AI to be trapped inside the mere body of a human? Or the question of, what would a multifarious consciousness spread around the galaxy be like as a leader? It could be something simpler about, what is it actually like to spend 10 minutes in a mall food court? Or, what is it actually like to be in a relationship? But the question is there and the investigation is there. The investigation is real. So yeah, I think that's the novelist's contribution here.
Yeah, and one of the things you said earlier, I want to go back to, is the inspirational nature of science fiction for people in STEM. I mean, I certainly went straight from Nancy Drew and the Hardy Boys to plowing my way through my dad's extensive sort of 1950s, 1960s sci-fi collection, which was interesting. I actually remember the specific moment I realized that there wasn't a moon base. Which was a crushing disappointment.
Yes, I can imagine.
So many people had written about it. I just assumed it must exist. And I think that process of having your imagination spark, that making you curious about how the world works, is a very much underappreciated part of science fiction.
And I guess I would add that I think the science fiction writers they're going out and getting something for us and sort of bringing it back, almost as if they're hunter-gatherers and they're exploring very strange terrain. I think of what they do. It's not merely that they conjure the consensus future. We all have sort of when you sit someone down and ask about the future, they talk about, spaceships and moon bases and possibly jetpacks and things like that. And that's all fine. I think if a science fiction writer just transcribes that, then they're not a very good science fiction writer at all. Instead, the function of the science fiction writer is to go further, go deeper, go weirder, and really kind of push the imagination into the far future in this way that I've come to think of as being very athletic, actually. I mean, I think there's sort of imaginative muscles involved. And by that standard, it's someone like Ann Leckie and her peers, they're like the sort of, the buff bodybuilders of this discipline. They have these huge, bulging imaginative muscles, and they're just kind of tossing, car tires around as if they were beanbags. And that's important. I think that's a real contribution to, certainly to just entertainment and the things that we all sort of get to add to our minds and our ways of thinking about the world. But then I think that is real work that actually has a real contribution to make to the kind of greater human intellectual enterprise as well.
Yeah. And I think I'm a very strong believer that the stories that we tell shape the way that we then shape the world. And one of the things that's really interesting about Leckie's work is that there's a gender question in her work, and she uses the pronoun she almost sort of throughout. And as someone who works with, concepts of gender a lot and gender and STEM, that feels kind of like actually very empowering for girls to read. I mean, role models do not have to be real people. They can be fictional people too. And an entire sort of world where, it's all she is in itself, I think, quite empowering.
I think that's exactly right. And again, it's the science fiction writer's job. We should expect that, honestly, of all good science fiction writers, men and women alike, to conjure a future like so many have done, through the whole course of the 20th century, that just reproduces the sort of depressing and frankly boring inequities and bullshit of our world. It's easy because you just kind of copy what you know, maybe without interrogating it or kind of prizing it apart to look at the gears inside. But yeah, the task at hand is to set those things on their head and make them strange. I mean, it's what I love about the pronoun in Leckie's books is that it is. I mean, of course, it is actually in our world very interesting and very political and really very laudable. It's like just a wonderful trick she plays. But in the fiction of the future world, the reason that our protagonist only uses she and her is that as a vast, powerful, potent AI, it basically can't tell the difference. It can't be bothered to tell the difference between men and women. It's almost like, me regarding a squirrel across the street. I'm like, I don't know. It's just a squirrel. Who even cares? And I think that to sort of flip that around and, show us ourselves through that lens of like, man, women, I don't know. I can't be bothered is just, it's lovely. It's one of the best things in fiction of any genre that I've encountered in years.
It is. It's great. It's great. I love it. But in terms of inspiration, like if you were going to send a copy of Ann Leckie's works to university departments, which subject areas do you think those people would get the most out of her work?
This might be a little too on point, but it's what occurs to me immediately. As you know, artificial intelligence is this thriving, percolating discipline right now. There's so much happening, and it's happening so fast. I think, based on my own observation, I think that actually many practitioners of these new machine learning and AI techniques are pretty thoughtful about things like gender and voice and who gets to speak and who's shaping this new technology. I would say significantly more so than average across these sort of technical disciplines. But even so, I think that people working on AI and machine learning now would probably benefit from reading Ancillary Justice and thinking about what it means to engage with strange minds, what the experience of the world for a strange mind might be. I think they would both enjoy it, and I think it might be a little bit productive. So I would buy boxes of Ancillary Justice and send it to all the big machine learning departments.
and of course, the question of the relationship between mind and body is a huge unanswered question, and the idea that we don't think with just our brains, that we think with our bodies is an area that is under exploration as we speak, because it is such a huge question.
And it actually makes me think of the sort of challenge facing science fiction writers, even sort of normal literary fiction writers writing stories that take place in our world today. They're actually being challenged by this new, I don't know what to call it, a new form of disembodied drama that's very common in all of our lives now. All the tools of fiction are about transcribing people talking to one another in space, moving through space, going on adventures, going down the street, going to the city next door, going into a warehouse with guns drawn or whatever it is. In fact, so many of the very interesting dramas in our lives now take place very quietly as we sit in front of a screen or maybe with a phone in our hands, and they all sort of look the same and no one is talking, so you can't really use quote marks. And it's interesting. Some people have called this sort of an emerging plot crisis in fiction, and I think it's also a crisis of sort of the punctuational and stylistic tools we use. And I think that actually does have something to do with minds and bodies, as more of the action now, especially the emotional action, takes place kind of exclusively in the realm of mind and text and symbol, and less in the realm of body. I think that actually there's some new inventions that need to be crafted for the fiction writers of the future.
And that is actually quite a stunning thought, because of course, when we talk about emotions and what we're thinking, we so often use physical sensation to describe it. Gut clenching is the first one that sort of springs to mind. But when you feel tense, even the word tense kind of makes your muscles kind of tense up. And so much of our emotional lives now is kind of slightly divorced from that physicality.
And it also, not only is the work and the experience more abstract, it's also more uniform. It'd be one thing if abstractly breaking up with someone looked totally different from abstractly deciding what rice cooker you're going to buy. But in fact, if someone was sitting on a couch, you wouldn't be sure. You really don't have a super good way of determining whether they are breaking up with someone or, shopping for a rice cooker. And that's very weird. The sort of collapse of so many different kinds of experience and intensities of experience into this activity that sort of always looks the same. And of course, that's just from the outside. The internal experience can still be tumultuous and, changing and everything else. But it's the depiction of that is challenging, and I think that there are people engaged in that project right now, and I think that as we, but truly not very many successful examples of doing it, at least not on the page. I think as we find those and as those depictions kind of roll out, I think they'll be useful, not only because they'll just be better and more believable representations of our life today, but they might teach us something about that life too. They might have something to reveal.
And I think this is where good science fiction, good fiction, poses questions that we don't have the answers to, that we then want to go away and say, how does this really work? What would the impact of this really be? And I think that's where authors like Ann Leckie are amazing, is the ability to pose those questions in a way that kind of really gets into your head and stays there.
Yeah, I always think of it as destabilizing, which I think is what you're talking about. A sense of posing a hard question, of complicating your view of the world and certainly of the future, and basically just kind of like making things weird, making things weirder. I think that's so many forces in our world, and many of them connected to STEM. Sort of forces of business and capitalism and markets and buying and selling things. They kind of want to push the other way. They want to make things seem like cool and normal and like, well, of course, that's how it works. Isn't it great? And now it's 20% off. I like things that push the other way. I like things that say, this is weird and it's about to get weirder.
Exactly. And when you get into the sort of real cutting edge of certain areas of science, weird doesn't really begin to cover it. We are finding out things about this world that are just totally gobsmacking. I guess, there's that, it is a two-way flow between, what science finds out and the questions that science is trying to answer, and then, how that is reflected by the fiction that is being written and that we're reading, and the questions that raises. I mean, as a teen and as a sort of young adult, my question always was, well, why isn't there a moon base? Because we can totally do that. And those questions, they're still being asked. They're hugely important in terms, I think, of steering not just sort of humanity's investigation of reality, but also on an individual level of, the questions that they pose for us as individuals, to say, what questions do I want to answer with my life? That's
right. And not only what questions do I want to answer, but what sort of visions do I want to realize? There are a few books, and I don't think that they're the best books, the best sci-fi books, but there are a few that have for years now acted as sort of templates for a lot of work, certainly in Silicon Valley and elsewhere too. I think of Snow Crash by Neil Stephenson, which conjured all this this crazy phantasmagorical sort of cyberpunk stuff in the future, and so many people sort of cite it as like, oh yes, ever since I read that, I wanted it to be real, and so I've worked on this 3D technology, or I've worked on these virtual reality goggles or whatever else, and that's all fine. But I think given that books sometimes do that, they sometimes fall into those slots for individuals or kind of for whole subcultures, I think we should all be very invested in maybe making some of those books more interesting and making some of those visions more interesting, so that they're not just visions of kind of material, technological things like moon bases and cool spaceships and VR goggles, but, some things that are more social, different social arrangements, things that are economic, things that are mental and cognitive, and things that are emotional too. I think we need those visions to steer towards as well.
Yeah, absolutely. Well, I think we will both highly recommend that everyone who hasn't read Ancillary Justice go out and do so immediately.
Yes, definitely. And if you like it, there's 2 more sequels, so you're all set.
Well, thank you so much for your time, Robin. It's been fascinating talking to you.
Real pleasure. Thank you for the invitation. I appreciate it.
Thanks to Robin for giving us his time today. If you'd like to find out more about Robin, you can visit his website at robinsloan.com or follow him on Twitter @RobinSloan. If you'd like to read Mr. Penumbra's 24-hour bookstore, it's available from Amazon, Barnes & Noble, iBooks, and of course from your local bookshop. So is Ann Leckie's Ancillary Justice. You can find out more about her and her books at annleckie.com, and you can follow her on Twitter at Ann_Leckie. That's Ann, ANN, Leckie, LECKIE. As ever, to make your life easier, we have all these links on our blog. Now it's time to announce the winner of March's competition. We had a copy of Dr. Helen Chersky's book, Storm in a Teacup, up for grabs, and the very lucky winner is Kirsty Burridge. Congratulations, Kirsty. Thanks again to our sponsor, ARM, for their ongoing support. If you'd like to join ARM as a podcast sponsor, please do get in touch. Thanks also to our editor, Andrew Marks. Don't forget that you can subscribe to our podcast on iTunes, Google Play and Stitcher. Please do rate, review and share our podcast with your friends. And thanks to everyone who's already helped us out with a review and a share. Next month, we'll be talking about building chemical sensors with an iPhone and duct tape with Dr. Rachel Burks. And we'll be talking about women in STEM with the head of the IET Library and Archives, Anne Locker. So thanks for listening and join us next month.